Hello once again, Machine Shop Math fans. Mchn1343. This is video 11, not video 9. So let's go over here and fix this. This is going to be V11 part 1. And it may just be one part. I don't know. We'll see. We have plenty of bandwidth. All right. This is dealing with speeds and feeds, which will be the extent of exam 4. Before you get started, you need to stop this video right now and go to this link in this PDF. It's an active link. You need to go to this link. It's here. It is a video from Haas Automation. Haas has a ton of instructional videos. And watch the video. Then come back to this video and finish this video and these review notes and lecture notes. Now, I want to make a note, and you need to understand this. We, for the purpose of this course, are going to use IPR. There are many ways to do this. If you go to carbidedepot.com, carbidedepot.com, and click on Technical Resources, you will see that there are all kinds of cross-reference charts. There's calculators, drill size charts, interactive drilling formula calculator, speeds and feeds for milling and tapping and turning and all that kind of good stuff. All right. Now, also under where is it? Interactive milling formula calculator, interactive math measurement and programming. There are G codes, interactive measurement conversion calculator, interactive trig calculator for right triangles only, of course. There are a lot of resources here at carbidedepot.com. There's a whole machining course in this. It'll teach you all about the different inserts. I would suggest that you bookmark this in your computer and use this as a future reference. All right, so that's carbidedepot.com. Now, this is going to be found in content, and the internet's slow today. Wow. This is going to be down here in week 6. See, exam 4. There's exam 4. Exam 4 is nothing but a long homework assignment. That's all it is. It's just a bunch of repetitive things, and we will go through everything that you're responsible for on exam 4. So let's get started. My advice is you do exam 4 pretty early. All right, so let's get back to our notes. All right, assuming you have watched this video and you have your master formula sheet printed out like I told you to. Speeds in customary units. These are metric units. These are customary units. We're going to be dealing in customary units. C is the cutting speed. It is not RPM. N is RPM. Remember the pulley problems? I use N as rotational speed. C is the cutting speed. So here's the parent formula. The cutting speed is pi times the diameter of the part, or if you're using a lathe, then it's the diameter of the part. If you're using a mill, then it's the diameter of the cutting tool. Or you're drilling, it's the diameter of the drill bit. That'd be the diameter, and there's N in RPMs, and 12 is to convert inches to feet. I've algebraically rearranged these formulas for you. Merry Christmas, so you don't have to do this. So the rotational speed of the tool or the lathe in RPM is 12 times the cutting speed divided by pi divided by d. Again, d is the size of the cutting tool in diameter or the diameter of the part if it's on a lathe. And if you're trying to solve for d, there's the formula for that. And here's the where. Cutting speed is in feet per minute or meters per minute. This is actually surface feet. So it's actually surface feet per minute. It would be the circumference of the tool or the part. Spindle speed in RPM and the diameter of the workpiece, lathe operation, or the diameter of the cutting tool, and that'll be in inches. Feeds, we will be doing IPR. There are many ways to do feeds. If you go back to Carbide Depot and look at all those different interactive formulas and calculators that they've got, you'll see that there's a way to do it for IPR, IPM, IPT, inches per tooth, inches per minute, feed rate, and inches per revolution. We will be dealing in IPR. And here's the where for all of that. Where you have feet in IPR, it's feet in revolutions per minute, inches per revolution, Then you have feed in inches per minute. You have feed in inches per tooth. You also have a CPT, the chip per tooth, and feed per tooth. And the number of teeth or flutes on the cutting, that's the cutting edges, and the spindle speed in RPM. Time is very important. We will be doing a lot of formulas dealing with time. So time, the parent formula, time is equal to L, the length of the cut or the depth of the hole, divided by the feed rate, divided by the RPM. Or if you're looking for length, then you have the time it took, the feed rate, and the RPM. This is your formula for the length. Algebraically rearranged for feed, it's L over Tn. Or if you're looking for RPM and you're given the length, the feed rate, and the time it took, that would be the RPM. Okay, where T is in minutes, time in minutes, length is in inches, F is feed rate in inches per revolution, and N is spindle speed in RPM. Here is a formula. We're going to derive this in this video. I will show you. It comes straight out of Trig. You'll see a lot of charts that for the extra Z depth for a pointed drill point, depending on the drill point angle. I mean, if you want a full diameter hole, a given depth, you can't use this as your depth, right? Because you're not going to get the full diameter of the hole. So you have to come up with a Z-add. A Z-add. That's what I call a Z-add. Remember that our X, Y, and Z, okay? If it's on a lathe, the turning part is on the Z-axis. If it's on a milling machine, the cutting tool is on the Z-axis. So when you do your touch-off and you want a full 1-inch hole, then you have to go 1 inch plus whatever this calculated depth is. Now I always add a couple of thousandths to that calculated Z depth so I get a good clean hole. And I also let the cutting tool or the drill bit hang down there. We call that the dwell time, for a few seconds to clear the hole out, make a good clean hole. But the formula is your Z-add is 1/2 the diameter divided by the tangent times 1/2 the drill point angle. So it's the tangent of 1/2 the drill point angle divided into half of the diameter of the hole, and that gives you your theoretical Z-add. All right, this should become more evident as we do the problems. So this is on page 20 of 22 of your master formula sheet. Okay, all right, so let's go to our notes and get started. All right, you have already watched the Haas speeds and feeds, and you remember that we're going to use IPR for this course. So let's solve the cutting speed. Let's solve for our theoretical cutting speed. Now you can look up the definition of cutting speed on Google, and it is a theoretical rule of thumb on what a given manufacturer recommends for a given material, and there are charts for these. I will give you the cutting speeds for the exam, if I am not mistaken. Let me look at the exam real quick. I think I gave you. Well, in the exam, there is a chart. Now, it's a rule of thumb chart, and it has a range of cutting speed. So if a particular operation, 70 to 130, then you take the average for your problem, and we'll go through that. We will go through that. All right. All right. All right. In fact, let's go to D2L and let's just look and see which version of this bloody test I put up here. Okay. Now, when you download this, it should be a form fillable PDF, and you're going to print. It. See, yeah, ignore the table on page 404 and use the C in the column. You'll have two answers for the calculated number. You'll have the total and then an example. Aluminum would be 650. Okay, we'll talk more about this later. See, I'll say use a cutting speed of 650, use 200, use 40, use 140, etc., etc. There's the chart. So this gives you an example. You see, in this particular operation, if we were going to use carbon steel, and it's going to be a milling operation, and we're going to use a high-speed steel tool to do the milling, the recommended cutting speed is from 70 to 130. You would just take the average of this. But I went ahead and did the averaging for you and put it on the exam. But this chart is not written in stone. It didn't come from the machining god. This is just something out of the old machining book. Your mileage is going to vary. The safest thing to do is go to your manufacturer of your insert or cutting tool and see what they recommend as a starting point for your cutting speed for that particular operation. And they may tell you to use 100, but it may not work good on your machine. You may have to go back up to 150, or you may have to slow it down a little bit. Your mileage is going to vary. These are a rule of thumb, a place to start. But if you do a calculation and you come up with a cutting speed of 55.77 feet per minute, surface feet per minute, that doesn't mean you're going to get a good cut. That doesn't mean you're going to get a good finish. What that does mean is that's a place to start. You got to do some trial cutting, and if this works for you, fine, you're lucky. If not, you may have to adjust this. You may have to bump your RPMs up or down or whatever, depending on the type of machine, the age of the machine, and a whole bunch of variables. All right? These calculations are a place to start. All right. So let's go through some problems. So let's solve for cutting speed. Here's our formula. N's the RPM, diameter, and C is the surface feet per minute. And let's pretend that our workpiece, our tool diameter, if it's a milling operation, we're dealing with the tool diameter. If we're lathe, it's the diameter of the piece. Then we're going to say it's this right here, 0.4631. And I just pull that number out of my tailpipe. All right, pi is pi. We're going to say we're going to use an RPM of 460, and we're going to divide by 12, and we end up getting a cutting speed of 55.77. Now, I'm not going to go to the calculator. You should be well enough into your calculator by now. You can do this simple formula here. Multiply across the top, divide by 12, and you're done. Now let's use the same parameters and let's solve for spindle speed. And this time we've changed the diameter, okay? We're going to say we got a cutting speed of 70, all right? let's say our manufacturer said, you're doing aluminum, you're doing something with aluminum or tool steel, and we recommend 70. All right, fine. You should have already watched the Haas video and seen what happens if you don't pay attention to your feed rates and your cutting speeds. You'll burn up a tool, tear up a part, and people will not be happy with you. They'll roll your toolbox out in the parking lot and tell you to go away and don't come back. All right, so we use the formula N equals 12 times the cutting speed, divided by pi, divided by 0.375, the diameter, right? There's the formula right there. All right, so that solves for N, the spindle speed. And if you wanted to solve for diameter, you come back up here and you'd use, or come back over here, the formula sheet, and you could use this if you were given the cutting speed and the RPMs, and you wanted to solve for the diameter, theoretical diameter. Now, in the CNC programming, if you use constant surface speed, most of your machines have a function that you can use constant surface speed. So let's say it's a lathe. Let's say it's a lathe operation. As the part gets smaller in diameter because you're turning it, it'll speed the machine up. Okay? As the diameter gets smaller, your RPMs will increase, right? So let's say you started out with 3 inches and you were your finished parts, I don't know, 2.5 inches. As you're turning it and it's getting smaller in diameter, you'll see the speed of the machine, the rotation speed will speed up. And that does that for you. Now, in a manual machine, you may have to stop somewhere in there and change the speed. All right? All right. So let's go back to our exam notes. All right. How about cutting time? Let's do a time formula. Sometimes you're going to need 2 formulas to solve these. Sometimes you will need 2 formulas to solve these. So our parent formula for cutting time is T equals the length of the cut divided by the feed rate divided by the spindle speed, N. Now you may have to go solve for spindle speed and then come plug the speed back in here to get the time. Or you may need the spindle speed, or you may need the diameter of the cut, so you'll have to use time to figure out your spindle speed and then go back up there and then look for and solve for diameter using the cutting speed formulas. All right, so let's say we have the number of cuts. Now this formula is only for 1 cut, so let's say we have 1 cut. Now if you've got 4 or 5 cuts, you got to multiply your time times 4 or 5, right? And let's say our feed rate is 0.002. Let's say the length of our cut is 20 inches. And let's say we started out with a spindle speed of 2100 RPM. Well, this is real hard, right? All you got to do is plug 20 inches into the L, plug in your feed rate, plug in your RPM, do your math, drive your calculator soberly. You don't want to be calculating intoxicated. And you come up with time in minutes. These all have units, right? Minutes. So it's 4.761905 minutes. It's not that difficult. Like I said, the test is really just a long homework assignment. It's just a repetitive set of problems. Here's a problem. Let's turn a 6-inch cylinder. It's 13 inches long. Let's say we use a cutting speed of 300. Now remember, your mileage is going to vary, but for this problem, we're going to use 300. And our cutting time is 1.5 minutes. So let's solve for F in IPR. So F, go back to master formula sheet, make sure we're using the right one. F, feed rate is L over Tn. L over Tn. F is L over Tn. Look at that. Okay, all right. At first, we're going to have to solve for N. At first, we have to solve for N. So, we were given the cutting speed. We use N equals 12C divided by pi d. 12C divided by pi d. And we come up with N. All right. So by doing that, doing this math, we end up with 190.9859317. Just go to 4 decimal places for this test. Now, in the real world, you're not going to plug in 190.9859. You'll round that puppy up to 191 in the real world, okay? Now, on my manual lathe, when I'm doing rifle barrels or doing any kind of turning, I can't hit 191 on my lathe. I think I get 170, 180, and then it jumps up over 200 because it's a manual machine. So, again, your mileage is going to vary. So if I'm in this range on my machine at home, now, yeah, theoretically, you could plug in the decimals, but people are going to laugh at you. Just round the puppy up to a whole number, all right? But for the sake of this test, go to 4 decimal places. All right, so we're going to use 190.9859, and we plug that in up here. All right, now that we've got our spindle speed, and we've got our time given to us, we've got our length of cut, we're going to find that our feed rate is 0.04537856 IPR. And that's what you would plug into your CNC line, or that's what you would set your machine up, your manual machine up, as a feed rate. If you've got a feed rate that's close to this, I think mine, I can get a 0.040 or 04 or something. I don't know. I don't have my chart with me. It's out in the shop. It's on the side of my lathe. But you would get close to this. And again, you're going to have to look and see what your cut looks like. Are you getting a good finish? Well, if that's the case, then leave everything alone. If not, you got to tweak something. That's the difference between being a cook and a chef. I went to the New Orleans School of Cooking many years ago, spent a whole 3 days there, and the chef, the master chef that taught us our cooking class, kept iterating the difference between a cook and a chef. A cook knows how, a chef knows why. So, a master machinist knows the why and the how, just like a master chef knows the how and the why. But a normal cook just knows the how. All right, enough of that. Okay, here's another problem. Let's combine drilling and counterbore operation. Okay. Now, the length per piece, per part, is 1.75 inches. The total time to do our operation is 7 hours for 2,500 pieces or parts. We set a spindle speed of 1,800 RPM. So our total parts is 2,500, yes? So we're going to solve for feed. All right, we're going to solve for feed. Now this is 7 hours for 2,500 pieces. So the first thing we got to do is we want to solve for feed rate, right? So feed is the L over Tn. So do we have this? We have the length, it's 1.375. We were given the RPM, yes. We were given the RPM. We don't have the time per part, so we got to come over here and look at our total time. Now we said it was going to be 7 hours for 2,500 parts, right? So we have 7 hours times 60 minutes per hour. So that's 7 hours over 1. We're multiplying fractions again, yeah, because this is 60 minutes per every hour. You multiply the tops across here, right? The hours cancel out. Hours cancel out. 7 hours is 420 minutes. And in 420 minutes, we did 2,500 parts. So we've got the time in minutes per part. It's a fraction. Time in minutes per part. You set your fraction up, and it tells you what you do. So time per part is 0.168 minutes. That's pretty fast. It must be like a Swiss machine or something, pumping these little puppies out. All right. So That's time per part. All right, so now you can plug your time back in here, time per part, and come up with a feed rate. Now your calculator is probably going to give you 4.546957672 raised to the negative 3. It may say E negative 3 or whatever. But you look at this, and all that means is you move the decimal place over 3 times. 1, 2, 3. So you got 2 zeros in front of the 4. So in normal decimal land, it's 0.004546957672. And yes, that's more decimal places than a human probably should need for this kind of stuff. All right. I would look at a feed rate of 0.004 to 0.005. Now, my manual machine will certainly do that. I know that for a fact. But your CNC machines might let you put in more than 4 or 5 decimal places. It doesn't really matter. You're going to have to look at your finish anyway. And everything goes into a finish. The type of lubricant you're using, the actual grade of material that you're using, the age of your machine, the age of the cutting tool. There are a lot of things. So your mileage is going to vary. So just get over it and expect this to be a journey. All right. It's just like long-range precision shooting. I can be shooting the same caliber, same barrel manufacturer as my competitor next to me, using the same bullets, and we got to tweak our loads a little different because of the tolerance in our 2 rifles. We might get close, but they may not be the same. All right. So just expect that. So play this part, play the video back over and over and over again. If you have questions, give me an email. Here's another problem. We're going to be using a milling cutter. It's a carbide, and we're going to use to mill 30 inches of stainless steel. Now, our time is 1.6 minutes. Our cutting speed is 325 feet per minute. The feed rate is 0.010 IPR. And what diameter mill is used? What diameter mill should we use? Well, okay. We go over and we look at our diameter formula in our master formula sheet. We're given speed, we're given cutting speed, so we're going to use this right here. The diameter is 12 times the cutting speed divided by pi divided by n. All right. So it's 12 times 325 feet per minute divided by pi and divided by n. Now we need an n. We weren't given an n here, so we're going to have to solve for n. So the first thing we do, we're going to use time formulas. We find n. We can use a time formula for n. We were given time, we were given length, we were given our feed rate, so we'll use a time formula for n. We got several formulas for n. Here's n right here. We were given this, we were given this, and we were given that. So we use this to find n, not this. Okay? In this conversation. So we do this. 30 inches divided by our feed rate, divided by the time, and we get a theoretical RPM of 1,875. And go plug this back in up here. And you'll end up, when you do the math, coming up with a diameter of 0.662. Now, I seriously doubt you're going to be able to find a mill that is exactly 0.662084563 in diameter. So what do? You go to the absolute nearest one you can get, and you go back through and figure out where your cutting speed is and your RPMs, and if you're still in the ballpark, you're okay. So again, this is a place to start. So what would 0.662084456 be in 16ths? Well, 0.66208 That's a little different today. 0.66208 divided by the decimal of 1/16. 1/16 is 0.0625. So how many sixteenths is that? Well, it looks like it's 10.5 sixteenths. So you could use a 10/16, which would be what? A 5/8. So you could pick up a 5/8 end mill and see if that would work for you. And I seriously doubt that a 1/2 16th is going to make a big difference. If it does, then you're probably doing something you're not supposed to be doing. So, if you really want to double check yourself, then you would go back in and redo this whole problem, going backwards, and say, okay, I've got to use a 5/8 inch end mill. What does that do for my cutting speed? Then with the RPM that you calculated, go see what the cutting speed is. You'd come back up here and see what your cutting speed is using that new diameter, and I bet you're going to find that it's so close to the cutting speed of 325 that it won't matter. What you would do then is go to the manufacturer of the end mill and see what range they recommend. They may even have a calculator on their website, and this becomes a moot point. All right, here's another problem. Base plates. Base plates. So we're going to take a base plate and we're going to punch or drill 6 holes in it. All right. Each plate has 6 375 thousandths holes. That's how many eighths? That's 3 eighths. Right. An eighth is 125 thou times 3. That's 375 thou. Or you could take 0.375 and divide it by 0.125, and you'd come up with 3. All right, so we're going to do 6 375 thousandths diameter holes, and they're through holes in each plate. We're going to use a feed rate of 0.004 IPR. We're going to use a cutting speed of 250 feet per minute because that's what the good fairy told us we could do. All right, the manufacturer of the drill bit. Setup and handling is 0.5 minutes per part. We have 850 plates total. 850 plates total. 850 plates total. Our drill point angle is 135 degrees. And we're going to solve for the total time in hours. Total time in hours. Hours, not minutes. Hours. Hours. Okay. And we know that the time formula gives it to us in minutes. All right. And we're going to do 850 plates. 850 plates. Now notice, we have added drill point angle. This will change the length of the drill. Has to travel down the z-axis, thus increasing the L length in our time formula, right? Okay. We want a full 375-inch diameter hole all the way through this 175. So, when we set our DRO on our manual mill, or we plug in our tool touch off and we get our total Z depth, we have to account for the thickness of the plate, 1.75, plus the depth of our drill point angle. Now, for the sake of this exam and in this class, we're going to use the exact Z calculated length. But in the real world, I would suggest you add a good 5 thousandths to this. That's what I do. That way, and you have to make sure your clearance, so you're not pecking your lathe table or your vise. Nothing pees me off more than to go back there and see little pecker holes in our vices and our milling tables. That just shows you had some moron using the machine. All right. So we've got to do that. That'll increase the length, right? Because the length is not 1.75. It'll be 1.75 plus whatever this is here. And in the real world, you'd add some more to it. But for the sake of this, we're just going to go down to here. So how did we get that formula in the first place? Well, we have to account for the drill point depth for a total Z, or we will not have a through hole. And you'll get laughed at and probably fired. All right. Now, so let's look at a typical drill point. Here's a diameter, and it's got an included angle. And this included angle is called the drill point angle. It's included because it goes from both sides, right? Now, your drill point angles are in all kinds of different angles. 135, 118, 105, who knows, okay? There's ways to calculate these. I've got a drill point angle measuring tool. And there are charts for standard drill point angles, but you may have one that is not in the chart, so then what do? Look like a goober in the machine shop? No. You only need this one formula. You only need this formula here forever and ever and ever. All right? So let's look at our right triangle. Okay? Our Z-add is the adjacent side of the angle, yeah? And 0.5D is the opposite side, right? Here's our Z depth. If this is our angle, this is half of the drill point angle. We have got what? We have a right triangle, do we not? We've made a right triangle. We split the diameter in half. We dropped a vertical line down, made a 90-degree angle right there. So the opposite side of that angle is 0.5D. The adjacent side is what we want to solve for. We know what this is because we have a 135-degree drill point. You divide that by 2, multiply it times 0.5. All right, so what do we use? We have to use tangent, right? You got angle, opposite, adjacent, angle, opposite, adjacent, angle, opposite, adjacent, angle, opposite, adjacent. You can only use one of the Holy Trinity, and there has to be tangent, some form of tangent, and we're actually solving for the adjacent side, which happens to be Z. Well, that's an ugly looking Z. All right. So the formula is adjacent equals opposite divided by the tangent of the angle. Now, we can change the name of adjacent to our Z-add. And our opposite side is 0.5D. So if it's a 1-inch or 2-inch drill or a 3/4 inch drill or a 3/8 inch drill, the D goes there. You multiply it by 0.5 and divide that by the tangent of half the drill point angle. So what's half of 135 degrees? Now the formula on the formula sheet, remember? That's how we got that formula. That's how I derived it. Okay. So our Z-add is 0.5 times 375, 0.375, divided by the tangent of 0.5 times 135. Now half of 135 is 67.5 degrees. So you multiply these two across the top, you get that number, 0.1875. And divide it by the tangent of 67.5 degrees, and voila, you have created the creme brulee. Right? You've got this answer right here. That's the theoretical additional depth that you've got to add to the plate thickness. So now with our Z-add, our plus Z of this, and our total L per hole is 175 plus our Z, that number there. So the length, now the theoretical length for our time formula is 1.827665043. All right? So we're going to say the length total per hole is 1.8277. We'll round this up to 4 decimal places. Okay? So we'll look at the 6 and the 5th. That'll go to a 7, and this is what we'll use, 1.8277. Now, in real life, we would add several thousandths. Again, I'm going to tell you this. And we're going to add dwell time to make sure we have a clean hole and a true hole. We don't have a little a little burr down at the bottom of the hole. Okay. All right. So let's reset it up. Now that we've calculated our additional length, remember this is our additional length per hole. That's our additional length per hole. And so our feed rate hadn't changed. This is our cutting speed. Setup and handling is 0.5 minutes per part. Our total plates is 850. Our drill diameter is this, and this is our total length. So we're going to solve for the total time. So time is the length divided by the feed rate divided by the N. Now, we got to solve for N, do we not? So we can first solve for N. The first thing we do is solve for N. So N is 12C divided by pi d. That's the original speed formula up here, right? N is 12C divided by pi d. All right. All right, so let's go back down here. And we get an N of this. This is the RPM for N. I'm not going to go through the math. You should be able to do this by now. If not, you got worse problems. The second thing we do, now this is our second step, is to adjust the L for each plate. We've done that, right? We've got the L, but we're going to do this 6 times per plate. So our total length is 1.8277 times 6. Now in the real world, we would add our dwell time to each hole, etc., but this is just a straightforward math problem. So let's take our length per hole, which includes our Z add, multiply it times 6, and we have our total length per plate of this. Do the math, multiply 6 times this. The third thing we do, our third step, is to solve for time per plate. Time per plate. Time per plate. So we have our total length divided by our feed rate divided by our N, plus we have to have our setup and handling per plate, right? So T, they're 10 inches, 10.9662 divided by 0.004 times our RPM, right? What was our RPM? Here's our RPM up here. Here's our RPM here. So multiply that times that. We get this divided by that. Okay. So multiply this times this, divide it into 10. You end up with this. We're going to add our half a minute, right? This is the time from just drilling the holes. We'll add our half a minute, and we get a total time per plate of 1.576604168 minutes, or something like that. Now we've got 850 plates. Okay, so the total time for 850 plates is going to be the time for one plate, which is 1.57766044168 times 850. So the total time is 1,340.113542 minutes, but we want the answer in hours, yes? So the time in hours is the time in minutes divided by 60 minutes per hour, yes? So you take 1,340.113542 minutes, divide that by 60, divide that by 60 minutes per hour. Minutes will cancel out, and you'll end up with 22.33522 and some change hours, whatever it is on your calculator, right? Now, we're gonna round that to 2 decimal places. Answer in 2 decimal places would be the total time is 22.34 hours to do 850 plates. Now, some of you more astute people are probably saying, well, you got to pick the drill up, the dwell time, move it over to the next hole. So in the real world, yeah, we would calculate all that moving time on the single plate, and that would be that. But for this problem, you use the parameters you're given, our setup and handling for each plate, and move on. So that's it. Exam 4 is fairly straightforward. Again, y'all can work ahead if you want. It's only 5 pages for the review. play this video back over and over again, and let's go back and look at the exam real quick to make sure I don't have any questions. Okay, I've given you the cutting speed to use in this. See, this is just a boring assignment. You do the calculation, blah 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 blah, over and over again, right? Okay, all right, and here are the problems that we went through, pretty much. Yeah, okay. Yeah, 850 plates. I did change this. Okay, good. So I didn't throw it away totally. And your drill point angle for the problem in the exam is 130 degrees. So you'll go through all of that. This should be pretty simple. Anyway, enjoy. We're at 45 minutes for this video, which seems to be about average. I will post this and we'll go from there. Well, good luck. Again, if you have any questions, reach out to me and we'll try to assuage your issues.